really quite straightforward. Right, so let's just do a wee example of this, and then I'll give you one to do. So, as we know, throughout the course of this year, we've spoken about exponentials all over the news, right? It's always to do with exponential rises in cases of COVID, and then what they hope for when they do a lockdown is that there's an exponential decrease in cases, right? So all this stuff to do with exponentials is actually really good for modelling situations like we've had this year, right? So this is an exponential graph question. Right, and if you've got a graphs question, it'll always tend to give you the form, okay? And passes through the point, and I'll always give you a coordinate point of some kind. Okay, and then I'll draw the graph for you. Yep, so making sure my graph's good, or my graph makes sense. It doesn't look that much like an exponential, but it will do. So this is like an exponential decrease, right? Exponential decrease graph, right? So I'm telling you, it's going through this point here, which is 2 along the way and 0.67667 up the way, right? A. Find the value of A to 1 decimal place. Right? Now, if you get a whole number answer, just give me a whole number answer, right? But I'm looking for 1 decimal place if you've got to do rounding, right? Because the question's saying that, right? Hence, find the equation of the graph. Okay, so the graph below has the form y equals ae to the power of negative x and passes through this point here. Okay, so it's an exponential graph, but you can see it's going down the way of the graph. It wants us to find the value of a to 1 decimal place, and hence find the equation of the graph. So the key word here is hence, right? Hence always means that whatever you've got as your previous answer, you're going to use it in part B, right? Keyword, right. Now, you would do the same in any graphs question at all, right? You've got the basic form, so you always write that down, right? Right. Now, what else do you know from the question, right? You know a point on that graph, right? And you know that a point is an x and a y. Right? That's what you know a point is. It's like if you're doing a straight line graph, you can put an x and a y into the form of it. And it just so happens that this is an exponential graph. But you do the same thing. Okay, so you take this bit of information, that x equals 2 and y equals 0.67667, and you put it into this form. So 0.67667 equals AE the power of negative 2. Okay, remember, I want to know what A is. Right, so I could work out e to the power of negative 2 in my calculator if I really wanted. Right, remember, to get e on your calculator, you press shift and then ln. Right, because ln and e are the opposite of each other. Right, so it's shift and then ln. Right, now I personally wouldn't do that, but if I did it like that, it would give me 0.135 and a whole lot of other stuff. What I'm going to do is, because I want to know what A is, and that A and that exponential are multiplying, I'm just going to take that exponential across and divide by it, like that. Because there's a wee multiply in there, so if you move it over to the other side, it becomes a divide. Right? So if I type that into my calculator, 0.67667 divided by e to the power of negative 2, so hopefully you can get that in your calculator. And hopefully your calculator gave you 4.999 and a whole lot of other stuff. Which, for my money, rounded to one decimal place, is 5.0. Okay, so I've just taken the form of the line that they always have to give you in the question. I suppose you could get you to see it from looking at it, but not really. Okay, now that's fine. Hence, so my form of my graph is a e to the power of negative x, but I've worked out that a is 5. So I'm just going to put 5.0 in place of a in my formula. So y is 5.0 e to the power of negative x. And that's the equation of my exponential graph. If you really wanted, you could write it as 5 e to the power of negative x. If you really wanted, but because it mentioned one decimal place in the previous part of the question, that's why I've kept it like that. Okay, so let's do another one. Okay, 2. I'm going to leave you to do this one yourself, or you start it anyway. The diagram below shows a graph of a function with the form y equals a e to the power of x, right? If it passes through negative 3, 0.6842, so let me draw it. Again, my drawings are, so I need to move that over. Okay, and now my point here is negative 3, 0.6842. So A, find the value of A and B, hence find the equation of the curve. Okay, go for it. You try it. I'll put the answer up in a couple of minutes because it shouldn't take you that long. Okay, so copy it if you want. Do the work in, see if you can get the answer for me. You have time to maybe have a wee look at it and try it. So same thing as always, right? Any graph type question, if you've got the form of it, now hopefully you can see this one's a rapid exponential increase, right? It's going up the way like that, whereas in the previous question, it was a rapid exponential decrease, right? Now, hopefully you can see that because that was a minus x, that caused the decrease. If the question gives you one with a positive x there, you'd expect it to be an increase like that. Okay? You don't need to know that. I'm just explaining why it is what it is. Right, so you substitute in your values there. So 0.6842 equals a e to the power of negative 3, because x is that's x, that's y. Right, same thing as before. So a is 0.6842 divided by e to the power of negative 3. So my calculator gave me a 13.742 and a whole lot of other stuff, and I wanted it to one decimal place, so that's just 13.7. So the whole point of that was so that I could work out what a was, right? Because all exponential graphs look the same roughly, but you can alter it by putting a number in front of it, right? And that's what we're doing, right? To create the graph there. So it's 13.7 e to the power of x. Okay, so hopefully you got that. Does anyone get any questions about that? Okay, so we go through logs and all these log rules, and logs are there to control exponentials, right? Now, any of these type of things in exponential, right? Y equals 2 to the power of x, y equals 5 to the power of x, right? When x is the power, that's when you've got an exponential, right? Now the ones that we've been looking at here is when we've got e to the power of x, right? Or when we've got something times e to the power of x. The last one was 5e to the power of negative x. So you can see in all of these, the x is the power, right? Now, in logs and exponentials in real life situations, this is the key exponential function, right? It models so many different situations in engineering, in science, in nature, in finance, right? Just like in a circle, the number pi, 3.1415, etc., models everything that you need to know about a circle, right? This letter E is everything we need to know about exponential growth, right? So the majority of the time when we're talking about exponentials, it's about this special exponential here, right? And remember, E, just like pi, they found the number pi to do with circles from doing lots of different experiments. Same with this, right? They found this letter E, or this number E, trying to model loads and loads of different situations. And E is just the number 2.7182818828 and so on forever. Right? The same way that pi goes on forever as well. Okay? So the majority of these questions that we deal with are all to do with this special exponential here. Okay? So that there really means 2.7182818828 to the power of x. Right? That's really what that means. But I ain't writing that number every time. So that's why they gave it the letter E. The same way, if you're doing a question with pi, you can't just use 3.14, because if you did that, none of our cars would work. Right? It needs to be more accurate than that. Okay, so all the logs and exponential questions we are going to do involve this special exponential. The other exponentials and logs we looked at in the previous videos, they're useful, but this is the one we need to know about. Okay, now, to control this exponential, we control it using a log, right? You control all exponentials using a log, right? I control this exponential here using log to the base 2, right? I would control this exponential here by using log to the base 5, right? I would control this exponential here by using log to the base e, right? But we don't call it log to the base e, we call it the natural log, right? It's the log we use all the time, because as I said, e models things that happen exponentially in nature. So that's why it's called ln, the natural log. Right? These two things are the same. Right? Log e and ln are the same thing. Okay? So this log to the base 2, we're not going to use that. This log to the base 5, we're not going to use that, because we're not talking about 2 to the power of x or 5 to the power of x. All of our situations are going to involve this number 2.718281828, but we call it e. Right? Now, everything's a lot more simple than it sounds. Right? So, in the last video, this is just me talking, right? I'm just trying to explain stuff rather than give you any great deal of notes on it, right? In the last video, I gave you these rules of logs, right? Okay? And that is if you take the log of an exponential, you just get the power, right? So here, if I start with 3 to the power of x, and I wanted to get x, I would take log to the base 3 of it, right? Okay, in the last video, don't worry about it. That means that see if I've got e to the power of x, and I want to know what x is, I take the natural log of it. Those two cancel out, and I'm left with just x, right? You'll see what I mean when I do it. Right, the other rules we need to know. If you add two logs, they've got the same base, you can multiply them inside one log. Okay? So here, these logs have got the same base. I'm adding them together, so I just multiply those two terms. So it give me log to the base a of 6x squared. Right? Here, remember ln just means log to the base e. So same thing, if I'm adding them together, I just multiply the two terms inside the log, so that gave me 24y cubed. Right? So if I'm adding two log terms with the same base, it's going to be ln, so it's going to be like these ones here. So if I'm adding two ln's together, I just multiply the numbers inside the ln, or the expressions inside the ln. Right? If I'm subtracting two logs with the same base, it becomes a divide. Right? We are going to be using ln. So I've got ln, and I'm subtracting them. So to put them into one log term, it becomes a divide. So 6x cubed divided by 2x gives me ln 3x squared. Okay? Now, key rule here. If I have a number in front of a log term, I can move that up to there and make it a power. Right? Or, if I've got a power and I don't want it there, I can move it to the front and make it a coefficient. Okay? So if we've got a number in front of a log, I can move it up and make it a power of the thing inside your log. And if we've got a power inside my log and I don't want it there, I can move it and make it a coefficient of the whole log term. Okay, these last ones you don't need to worry about. It's not going to come up. This last one is why that first rule works. Okay, so all you need to know is if you're adding logs, it becomes a multiply. If you're taking away logs, it becomes a divide. And if you take the log of an exponential, they cancel each other off. Right? Now, if you watched the video from last week, you'll have seen that already. So let's do loads of examples. We're going to just deal with formula, right? As I said, I'm recording this, so don't worry if you feel like you've missed anything, right? Transposing. And I did this at the end of the last video as well. But I just want to be sure because I didn't take the class because I was ill. I took you for your test, but by the end of that point I couldn't talk, and I still can't talk that well, but doing the best I can. Right, so if you're transposing formula with ln, okay, so if you're transposing a formula with ln, you want to isolate the ln as one term if possible. Well, it's always going to be possible. And you want to take the exponential of both sides. So, in fact, I'll do a full example. Right. So we've got this formula here for something, right? I've totally made it up. 2 ln x plus ln 4x, and I want to make x the subject of the formula, and b, find the value of x when p equals 2.54, right? Now, this isn't a formula for anything, but there's loads of formulas out there which have ln in them, right? They're just a bit too complicated to do for our first couple of examples, okay? Let me just get one up. Right, so you know if you want to make x the subject of a formula, if you want to make something the subject of a formula, what you want to do is make that formula x equals something, right? Because let's say that's I don't know what p is. P is a variable, right? And x is another variable. I'm not wanting to work out p just now because I've got a value for p. I want to work out what x is, right? So what I always do is when I'm transposing a formula, changing the subject of a formula, is I always flip the sides round so that the thing I want is on the correct side, right? And that's what we've done throughout this course, right? I want it to be x equals, so I'm just switching the sides of the formula. Now, what I want to do is I want to merge those two log terms together. So I want to merge those two ln terms together. Now, let's look at the rules. Right? This is my rule here. If I've got two log terms and I've got the same base, well they do, ln means log to the base e, right? So these are both log to the base e, so they've got the same base. I can multiply them, but I can only do that if it's just log and log, or ln and ln. If there is a number in front of either of them, you cannot do it, right? So hopefully you can see that in my example here, I've got a 2 here in front of my log. So I can't combine those two logs together yet. So I've got a rule though, remember, that I can take a number from in front of a log and make it the power of the expression inside the log. Okay? So I can move that 2 from here and put it up to here. Okay? So ln x squared plus ln 4x equals p. And now I can combine those log terms together because there's no numbers in front of them. It's exactly the way I want it, right? So that's ln x squared times 4x, which is 4x cubed equals p. Okay, so now what I've done is I've isolated the ln. That means I've only got one ln term, right? And when I get to that point, now this is not wholly mathematically great, but I like it because it makes a lot of sense to people, right? What we're going to do is we're going to take the exponential of both sides, right? So that means we're going to take the exponential of that side like that, and I'm going to take the exponential of that side like that. Now, the reason that the e is as large is that that p is becoming a power. Because when you take the exponential of something, it becomes a power. Okay? Now, what happens here is these two cancel off and your 4x cubed drops down. So 4x cubed equals e to the power of p. So the p needs to look like a power. You can't just write ep, e to the power of p. So I'm nearly there. I've just got to get rid of my 4 and I've got to get rid of my cubed. So I'll move my 4 over, so that becomes divide by 4. And if you move a cubed over, it becomes not square root, it becomes cube root. Like that. And try and make that p look like a power, because that's where loads of people tend to lose marks in the test. Right, so what I've done there is, I'll let you copy that, hopefully you've got that. Right, so what I've now done is I've created a new formula, right? X is equal to this, right? And what I've said is, like, I want to use your new formula to work out the value of x when p is 2.54. So that's all I'm going to do. Square root of e to the power of 2.54 divided by 4. Now, personally, if I was typing this into my calculator, I would be pressing shift, square root, because that gives you the cube root. Then I'd be pressing my wee fraction button. This is only if you've got a Casio calculator, by the way. If you've got a different calculator, you might struggle. Fraction button, which remember is below ABS. Right? Then I would type in shift ln, because that would give me my exponential. Then I would type in my 2.54. Then I'd press down on the wee D-pad thing, at the top, twice, to take me down to the bottom, and then I'd type in 4. Like, that's how I type that into calculator. Now I know Chris, who had you last year, can put the calculator up on screen. I've got a MacBook, so it doesn't. There's no calculator, Casio calculator app for a MacBook, unfortunately. So that's why I've got to write out the buttons. So hopefully you can type that into your calculator, and I got that to be 1.468, which is 1.47. Like that. Okay, so probably the most useful application of ln in natural logs is for stuff like half-lives and decay. Now I'm trying to find a good... There's a couple of good questions in this from higher maths, but I'll maybe put that up later on. I would rather be just focused on getting this stuff done. Right, okay, let's do another example 2. V equals 2 ln x plus 2 ln, let's have a look, 4x, yeah, a, make x the subject, b, find a value for x when v equals, like, let's see, what's this going to be? Cool. 6.25. Right. Slightly changed my example from the one I did with the previous class, but hey. So, first thing I'm going to do is I'm going to just switch my formula around so that I can do stuff with it. Okay. Now, what I need to do is I can't use my rules to push my ln's together because of these two coefficients of 2, right? But this is where we've got to watch, okay? Remember, x is the thing inside the log here, and 4x is the thing inside the log there, right? So let's move that 2 up. So that's going to be ln x squared plus ln why is that wrong?
Not with 2 times 4 as well?
Not 2 times 4, but you're close. It's 4 squared as well. So you need to put it in a bracket like that. Perfect, yeah. So watch that. If you're moving something from the front and making it a power, and is a number as well as a letter, you need to square the number and square the letter, right? So don't miss that out, right? I don't actually think it comes up, but I just want to make sure that you know that if you get situations like that, you need to make sure you square everything that's inside your log term, okay? So that's ln x squared plus ln, and remember 4 squared is 16, so it's 16 x squared equals v. Okay, now because I've got ln terms on their own, I can push them together. So that's ln 16 x to the power of 4 equals v. And that's what you want. You want your ln isolated as one term, preferably in the left-hand side, because that then allows me to go, right, I'm taking the exponential of this side and the exponential of this side. Now, we know what happens next. The e and the ln cancel each other out, and your 16x to the power of 4 drops. I'll explain why that is, right? But just treat the rule like that. Gives you e to the power of v. So, same thing as before. I need to this time divide by 16. And rather than finding, take the power of 4 across, rather than finding the square root, the cube root, this time it's the 4th root of e to the power of v over 16. And if you're looking to put a different root into the calculator, right, where you've got to choose it, it's shift. And then your x with the wee box symbol there, like that. Okay? That allows you to put any number you want in your root. Right, now, as I said, I want to explain why this works, right? I'm not going to ask you why it works or whatever, right? So see here, right? E to the power of ln 16x to the power of 4 equals e to the power of v, right? And what I've told you is these two cancel off and that drops down, right? But what really happens is that these two cancel off and become 1, and that 16x to the power of 4 comes to the front. But you don't need to know that, right? Because e and ln just becomes 1. Okay, but I'm not going to ask you that. Just treat it as this. E and ln cancel out, and that pops down. Okay, one last one in this, and then I'll. Yeah, one last one, and I'll give. In fact, I'll put 2 up for you. I never did the last bit, did I? Sorry. Find the value of x when v is 6.25. Right, let's do that. Right, I'll just practice this going into your calculator. So it's the 4th root of e to the power of 6.25 over 16. Yes, let's see if we can get that into our calculator. So I'm going to press shift that, shift and then that root button, then I'll put my 4 in, then I'll go long. I think I'll put my fraction button in next. Then shift and LN gives me my exponential, 6.25 and 16. Right. And that, my calculator gives me 2.385, which is 2.39. Okay. Again, I'll write out the buttons I pressed just in case you haven't got it. Shift. Then I pressed, what was that? I pressed a long to go inside my fourth root. Then I pressed my fraction button, set up a fraction. Then I put in shift ln to give me my exponential. Then I put in 6.25. 6.25 is not a button, but you know what I mean. Then I press down twice again. And then I put in 16. That's how I put it into my calculator, I think. And that's how I got my answer. I love the fraction button in these calculators. Makes my life so much easier. Okay. Is anyone getting questions about that or can't get it working in their calculator? No? Cool. Right. So, as I say, like 3. So t equals 2 ln 3x take away ln x, make x the subject, find the value for x when t equals 3.72, and then 4 L equals why not? Okay, there you go. 2 questions. Can you please try that the same way as I did? I'll go through the answers at 10 past or something, just before 10 past. Either of them.
All good, I think.
You're all good? Cool. Right, if anybody wants me to go over any of these at the end, because you don't want to say just now, that's fine. I will do that. Now, log formulas are not that useful, right? Because they're not that good at modelling situations. The best things are exponential formulas. Because as I said, exponential formulas can be used to model half-lives of radiation. So if you end up working in nuclear, reactors or nuclear engineering, you'll be doing a lot of stuff involving half-lives. They involve negative exponential growth, so negative decay, or positive growth depending on what you're using them for. Okay. So if you're looking to create energy, you'll get exponential growth because you want to create masses of energy. And you're hoping that you can get the material to degrade quickly, that you can get rid of it. It's unlikely, but that's what you're looking to do. So let's look at formula with exponentials then, right? Now, what we want to do is very similar to what we did with logs. Right, so just like we did with logs, we're going to isolate the exponential and then take ln of both sides. Okay, so you want to isolate the exponential if you can, and then take the natural log ln of both sides. And as I said, I think these are actually nicer and easier than the last lot, and they're more useful. I'll just make x the subject. Y equals 40 e to the power of 4x. So what I would do is I would switch everything round again so the letter I want's on the right side. I want it to be x equals, so I'll flip round the formula, right? So 40e to the power of 4x equals y. Right, now what I would love to do at this point is go, right, don't copy this. So I'm just showing, I'd like to go ln and ln. Oh, that ln cancels out with that e. It doesn't. There's that 40 in the way. So I can't take the natural log it because that 40 is a big barrier to what I'm trying to do. So let's go back to what I had. So I need to move that 40 first. Right, I know that's multiplying the e to the power of 4x. So if I move it across, it just becomes y divided by 40. Right, and now I've isolated the exponential. It's just an exponential, there's nothing in front of it. Right, so I'm just going to leave enough space. So I'm going to take the natural log of both sides, ln and ln. Now, on this right hand side, I would always put what's there in a bracket, right? It just keeps everything nice. Now, that thing in the bracket is not a power. When you take the ln of something, it doesn't become a power, right? When you take the exponential, it becomes a power. When you take the log, it doesn't. Now, exact same process in this, or the exact same thing happens in this left hand side. Your ln and your e cancel off and your 4x drops down. So 4x equals ln y over 40. Okay, And then all you need to do is divide that by 4. So ln y take away 40 over 4. And that's you done. Now, I obviously could then say to you, find the value of x when y equals 17. And you put 17 into there and then type it into your calculator. Okay, let's look at another one. Two. Make x the subject. So p equals 6t plus e to the power of nx. Okay. I want to make x the subject. So again, first thing I'm going to do is do that. Now, this time, the thing that's I don't like is the fact we got a 6t here. So I'll just do what I normally do in an equation. 6t, if I move that over, that becomes take away 6t. Like that. And now I'm ready to take the natural log, or ln, of both sides. ln, and remember, just put a bracket around it. It just means you're right because you're taking the natural log of everything there. Right, so a bracket always helps us. So your ln and your exponential cancel, and your nx drops down. So we're left with that formula there. My ln's are beginning to like h's again. I'm sorry. I will change that. I've got this awful habit of writing an ln so fast. It begins to look like an h. Right. So I want to know x. I've just got to divide by that n there. So it's ln p take away 6t for n. And notice that ln means natural log. It's nothing to do with that n there. Right. Don't cancel them off. ln stands for natural log. N just the letter n. Okay, I'll do one more like this and then I'll do a question in context for us to look at. I'll give you a few to try and then we'll do some practice of everything. Okay? Right. If you want to go ahead and try this one first, then feel free. So p equals negative 4e to the power of 4t squared take away 9. Make t the subject of the formula. B, find the value of t when p equals, what did I put? Negative 32. Yeah, negative 32. See if you want to have a wee go at that and see how you get on. I'll go over it at 22 minutes past. I'll give you 4 minutes. See how you do. Right? Don't be scared to get things wrong. You get stuff wrong, you learn from it. then. So first thing I did, or I would do, is rewrite it. Now, so negative 4 negative 4 e to the power of 4t squared take away 9 equals p. So I need to move that negative 4. So that negative 4 is multiplying that e. So it's going to be p divided by minus 4 like that. Okay, not p add 4. You're doing the opposite. And don't change it from a negative to a positive. You're doing the opposite. The opposite of multiplying by negative 4 is dividing by negative 4. Right? Too many people just change the sign because you don't change the sign. So watch that. Okay. Now, you should never have a negative in the bottom of a fraction if you can avoid it. Right? So what I would do here, just to make this more mathematically right, before I took my ln, if the top's positive and the bottom's negative, the whole thing just becomes negative. So it's negative p over 4 like that. That's what I would have done, or move the negative onto the top, either one. Because you'd never have a negative in the bottom of a fraction. Anyway, now take the ln of both sides. So ln e to the power of 4t squared, take away 9, equals ln negative p over 4, like that. And then these two cancel off, and I'm left with 4t squared, take away 9, equals ln negative p over 4. I just check, that might be my door. Right. Apologies, I'm not waiting for anything, but I just thought somebody knocked my door there. Anyway, obviously not. So, you move the 9 across, and it becomes, it's a takeaway 9, so it becomes add 9 on the other side. So, we're then dividing by 4 because that's multiplying the t. And lastly, hopefully, you should be getting a square root like that. Just like that. Now that is really tough. Right, I made that as difficult as I possibly could for you there. Right, so if you got that, or even if you left the negative on the bottom of the 4, you'd still get full marks with that. Yeah, I was just being picky there. Okay, then when I substituted that all in, now I know I again would make sure I use my fraction button twice. I used my fraction button in there, and I did use my fraction button in there. Anyway, so that would be the square root of ln. If I put negative 32 in here, it just becomes 32. So it's 32 over 4 plus 9 over 4. And I got that when I typed it into my calculator to be 1.664, which is 1.66. Does anyone have any questions about that? Did anyone get anything different or want me to explain anything? Cool. Right, hopefully that's a no. Right, what I'll do is, what I want to do is I'll show you an actual situation where this is used, right? So here we go. As I said, it can be used in nuclear science, so radiation, stuff like that. Right, so the amount of micrograms of a certain radioactive substance remaining after t years decreases according to this formula here, right? AT equals A0 e to the power of negative 0.002t, where A0 is the amount present initially. If 600 grams are left after 1,000 years, how many micrograms were present initially? Right? So hopefully you can see that I've got a formula here involving an exponential. Now, I'm not going to give you a question that has got a context like this, but this is the kind of context you can apply these problems to. Right, so I'm going to talk through it and go over it. Now, this question here is actually from a really old higher maths paper from 2004. So it was a year before I sat higher maths. So let's have a wee look at it. Now, if you want to copy it, fine. Don't need to. Might confuse you. But I just want to show you that this can be used. I'm not just teaching you this stuff because it's part of the syllabus. I'm teaching you because it could come up and you could use it in a project, you can use it in a job, you can use it anywhere where an exponential is used to model a decrease or an increase. Right? So, remember, AT is the amount left after a certain period of time. Right? So in part A, AT is 600, right? And T is my time, is 1,000, right? So, part A. 1,000 equals A0, which is my original amount, e to the power of negative 0.002 times 1,000. Okay? So, 1,000 equals A0 e to the power of negative, and I'm just going to put that bit there in. Negative 0.002 times 1,000. I think that's going to give me negative 2. So that's e to the power of negative 2. Yes.
Did you not say that the AT was 600?
Oh, 600. Where have I got 1,000 from? Oh, I'm an Egypt. Thank you. I can't read. I do that from time to time. I say something and then I write down something else. Thanks. Thanks very much for doing that, for correcting me.
Please.
Going off the habit of doing that. Right. So then we divide through by that, the e to the power of negative 2. And hopefully you can see it now kind of looks like that graph question I was doing at the start, where I wanted to work out the value in there. Right? I'm just applying it to an actual real life application now. Okay, so 600 divided by e to the power of negative 2 gives me 4,433.43. Okay. B. Right, so let's write my formula again. So AT A0 e to the power of negative 0.002t. Right, so now we've done part A, right? So just like in that graphs question at the start, I now know the exact formula for this substance, right? That is, the AT is 4,433.43 or 0.4, depending if they want it to 1 decimal place or 2 decimal places. I gave that to 2 decimal places. It doesn't say anything in the question, does it? No. Okay. E to the power of negative 0.002t. Right? That's what I know that for this specific substance, when I had this amount available at the start. I want to know after how long I have half of this, right? So let's work that out. So 4433.43 divided by 2. So I want to know when I've got half of this. Right, so half of that would be 2216.715 equals 4433.43 e to the power of negative 0.002t. Right? Hopefully you can now see that I now have an equation and I'm wanting to work out what t is. Right? Okay, so let's flip it around. So 4433.43 e to the power of negative 0.002t equals 2216.715. And what I want this to look like at the end is t equals and then my answer. So I'm transposing this question to get an t equals. Right, just like I've been doing in the last set of questions. Okay, so I want to take ln of this bit here because I want to get rid of that e because I want to know what t is. But I can't because of this number here. Now, if you were really clever at the start, you could have got to this stage straight away. But this is the way I would have done it when I was doing this type of question when I was learning exponentials. Now, if I type that bit into my calculator, it gives me 0.5. Why does it give me 0.5?
It's half.
Because it's the half-life. Exactly, spot on. Because it was the half-life. That's what I want to work out. Remember, the whole point of this was, what's the half-life of the substance? How long does it take for it to half? Right? I started with the initial amount, decided to half it, so I shouldn't have been surprised that when I divided them, I got 0.5. But now I'm just going to take ln of both sides. Like that there. And as usual, your ln and your e cancel off and that drops down. Like that. So I've got one last thing to do, and that's divide through by negative 0.002. And the time it's taken for this half-life of this substance is 346.57 years. Okay, and that's why we've got to watch what hopefully you know with certain nuclear materials, depleted uranium, all that kind of stuff. The half-lives are huge. It takes a long time, way beyond our lifetimes, for us to get rid of that waste, for that waste to become safe. Okay, so hopefully what I've done there is not confuse you. I've hopefully shown you that this stuff can be used to model real life situations. So I took a formula which involved an exponential. I transposed it, and that allowed me to work out that the time was 346 years, 347 years, whatever you want it to be. Right, now all I'm going to do is I'm going to give you a few of those exponential formulas to transpose, and then, as I said, I'll give you a few practice questions to work on, and then I'll give you the answers to those, and then I'll let you go away and practice the questions that are up on Teams. Okay, so that was another one. That's not what I wanted to do, but this is another one. I'm not going to do it. Again, nuclear generator, electrical power can be modelled by this situation, right? So again, nuclear power, again, is from a higher maths question, but I just wanted to show you another context, but I'm not going to do that question because it's not going to be that difficult, the stuff you've got to do. Right, so let's make my questions the same as my last class so that I've got the answers here. Right, questions. So make t the subject, so y equals 10e to the power of 4t at t is awful. Right, 2. Then I want you to do y equals 16e to the power of negative 4t squared. Right, I want you to make t the subject. Then 3, y equals 6p plus 4e to the power of 3t, and then lastly y equals 32e to the power of 4t take away 2, right? And okay, so I'll give you until 10 to or something. Just let me know when you've finished the questions in the chat or whatever, right? So we're not just sitting about doing nothing, right? So I'll try and go through them at 10 to, but if you finish before then, or if you feel like you need more time, please tell me. Practice questions number 1 is obviously going to be 1, which looks like a graph. He says it's going to the wrong slide. There we go. So these are your practice questions. I'll move my wee thing out the way. Oh, what's going on here? Right, so the graph has the form y equals ae to the power of x. Can you find the value of a to 1 decimal place, and then hence find the equation of that graph? Then I've got 2 ln 6y squared, take away ln 9y squared equals x. Can you please make y the subject of the formula, and then find y when x is 18.64. After about 4 or 5 minutes, I'll move the page down and I'll put it on the third question for you. Okay, so please try these 2 questions, and then I'll move it down after about 5 minutes to reveal the third question. Anyway, so that's the last one. So flipped my formula around, moved my 8 across, took ln of both sides, so I got 5t plus 4 equals ln z over 8. I subtracted 4, I moved that across and subtracted it, and then divided by 5. And I was left with that as my new formula with t as the subject. And then I got t to be negative 0.86. And I substituted it in. Okay, so hopefully you got that. Has anyone got any questions about that one? Are we alright? So, first question is the graphs question. We've got a to be 5.6 and y equals 5.6 e to the power of x. Then 2, I got y equals the square root, and make sure the square root looks like it's going around everything, e to the power of x over 4. When I substituted in my 18.64, I get 5,579.49. And then the last one, I transposed my formula. I got this thing here, and that gave me t to be negative 0.86. Right, so that's all the stuff you need to know. Now,